is to make consistency of the styles, the italics and other styles for all these sub-formula type things.
Yeah, right.
Yeah. All right. Anyway, so we go on here. One thing we're going to need here is these ribbons, so that it doesn't look like they're all just, so it doesn't look like it's just blue there. It should be all the blue and red should both be there.
I know. Yeah.
And yeah, I mean, there's some simple things here. I don't quite know what this, what we probably should do here. I see. There's also the possibility of longer proofs. Well, that's all right. It's okay. Okay, let's get into the real stuff here. I don't know what we're doing up with this. Whatever we do for the ribbons there, we should do the same ribboning here.
Yes. Yeah, I understand.
And I don't really know what this.
Are we just comparing this with other paths here?
Yeah. We're comparing it with some longer paths. I don't know why we're saying. I don't know why we'd say no frame ticks on the x-axis. Yeah, and there should only be ticks. Okay, well, anyway, I mean, this is some, okay, let's get to work. I don't know, again, I don't really understand the role of this one.
Neither do I.
That one, it goes to 7. I'm not sure, Okay, so now okay, so what we're saying here is, the claim is right here that A equals B dot A gives us this. So should we be using, we've already talked about bi-substitution at this point. Yes. So should we from the get-go use bi-substitution here?
Why not?
Okay.
That seems right.
So so do we just add a B here? Is that right?
Well, as a general convention, Nick, we should just use the cumulative token event graph and use the bi-substitution option, right?
Yeah. With the B.
Cumulative token event graph. 1, B there. Is that correct?
Right.
Okay.
Now, I've seen comments before where Stephen, you don't like that the root vertex is kind of off to the side here, right?
I don't. I
So
would
let's
like it
just
to be above.
establish the conventional code for, using the root vertex option, putting that on top, because we've done it before.
Yeah, okay. Well, fine.
So Nick, what do we do here?
Well, in this case, maybe identity goes to false would be better.
Oh, okay.
What do we want to say?
Identity goes to false. Sure, it doesn't. No, it's not.
Okay. Okay, hold on. Let's just make a comment here. Put the root vertex on top. Now, the other question is whether we're going to color, and this is a general thing, whether we're going to color the axiom that we use a slightly different color.
The green. Yeah, I think we should.
I think it should be slightly green. Okay, so we're going to need a color for that, and we're going to need to apply that.
Everywhere. Yeah.
Yeah. Okay. So after 2 steps, that shows up in the entailment cone. Okay, so let's look at that. Where is that? Why didn't this show up? Well, let's try it again. Let's try it with a cumulative token event graph. Oh gosh, maybe B will do something completely different here now.
There you go.
Okay. This isn't very beautiful though. I mean, in other words,
No.
why does this,
No,
why
it's
does it
not.
have? So what happens if I remove that? Oh, for God's sake. Okay, what happens if I say graph? How can I get this less bushy, less stuffy? I mean, I don't even understand what's happening here.
Why are all the events on top? It's like an event sandwich. This isn't what we want at all.
Yeah, but what? No, it isn't. But what? How would we get rid of the events here altogether? Except we don't want to do that because we want to show the events. Look, well, we want something where when we extract this subgraph, okay, how can we make this a more reasonable looking thing?
Use find proof and find what you're open for.
No, I'm not. I'm just saying the layout of this picture should look more like this as an actual thing where there are events and there are things coming out of the events rather than this weird, do you get what I'm saying? The weird thing with the events at the bottom and everything going back to the events.
No, the events are at the top as well.
I know.
The tokens are in the middle. Okay, Nick, so what happens if we use the root option here? Would it push all the what would it do? Would it help?
I think it's the default. It's like what it should be.
But, yeah, but clearly
it's clearly not, right?
Clearly this is wrong. So
yeah, well, you can try it to other root vertex. Yeah, see what happens.
But look, the main point is that we want the events in the middle, like in this picture here.
Yes.
Let's see what happens if we go to pure substitution. I suspect we're going to lose the actual node. Why the hell are the events? I mean, that's better, but why the hell are the events in the middle?
Nick, you got me. You have any insights?
We need a layout where the events at generation n are at a certain height. And I think there's a way to do that.
There's
See what
no
I'm saying?
generation.
What's that?
There's no notion of generation. They just combine pairwise.
Yeah, but there's, I think we've got you up in the middle of your night, and this is terrible. But no, I'm saying that there is a notion of which state you have now reached. You get what I'm saying?
Sure. Yes.
Yeah. Well,
And so what I'm saying is that, and so what we want to do is we want to draw, going down the page, the events that you reach on step 0, 1, 2. Am I making sense? Like we have here, this is 0, 1, 2, except that for some bizarre reason, the events are above them. You know what I'm saying?
Have we ever seen this before, though? I haven't seen this before.
I've seen this problem before.
You have? Okay.
Yeah.
we can make a custom layout. Or
Yeah,
just
that's what
other foliation. So
yeah, that's what I'm thinking. Right. Okay, in any case, all right. So we're gonna make a
Okay.
Okay, so here, if we wanted the path from the root vertex to this, we would have a single path from the root vertex. No, well, what would the subgraph be? Because that's what we're about to pull out here. Do you see what I'm saying?
Yes.
Where's edge fix? What's edge fix now called?
two-way rule fix maybe.
Say it again.
Two-way rule fix.
Lowercase t. Yes. Okay.
So this should be, these are different, aren't they? Yes, they are different. Okay, this sizing is, well, whatever, but we can deal with that later. Okay, so now are we going to indicate okay, so now here, how would we indicate that path on this?
It's just a subgraph.
No, I know.
Yeah.
So you think we should just take this result here and just highlight those subgraphs? Is that right?
Why not?
Right?
Yeah. Okay, but let's look at the flow of what we're saying here. Okay, now we say there are multiple paths to reach this statement. Now, is this all of the paths, or would there be even more paths? Well, there are multiple paths. For example, how
can we check? How can we check to see if
well,
we have
hold
all
on,
of
hold
them?
on. Let's see. There are multiple paths to reach this statement. Here are, well, I mean, clearly you can have an infinite number if you go further forward. What's that 3 here? Is that the number of proofs or what? No.
No.
It's a number of steps.
So is this all the proofs of 3 steps?
You can try more. I think it's if you add O after your B. Or where is it? No, this 3 is already a number of proofs.
That 3 is? But we've got 4
We have
proofs.
4.
You have 2 for number of steps and 3. I don't know why I found 3, but it is a argument for a count of proofs.
Okay.
Well, are these all different?
Should be. Maybe the events are different.
What's the difference between
Yeah, they're different.
4 and 4?
Oh my God. How many of these are there?
Can you say all? Does that work? Instead of 10? Instead of giving you a number?
Well, but let's just see. If we do vertex list / at that, and then we
There-
say,
Too many repetitions. Because you have 3 steps of evolution, or 2 steps. They're like the same event happens twice. That's weird.
well, what are you saying? Are you saying that is there an event deduplication issue here or something?
Yeah. But yeah.
But so are these in fact distinct or not?
In fact, what?
Are these in fact distinct or not?
They're distinct in a sense that events are different. But if you add the duplication of events, maybe there's going to be less. There's going to be less.
So what happens if I say, what do I say here? Event deduplication to true?
Yeah. If it works, I think it. Yeah, it should.
There's only one proof according to that.
Yeah.
But these are distinctly different. A, B, B, C, A.
It's the same one.
It's the same proof.
They're all the same. Just yeah, I think it's the same proof all over again.
I can't tell because there's overlap between the vertices.
Yeah, but look, the fact that these are 2 distinct events here. In the theorem prover, does it do event deduplication or not?
Like in what prover?
Well, in the find equational proof followed by your proof graph to token event graph.
Well, if you do find the equational proof, of course, there's no duplication. But if you just find the cumulative proof, there is no find equational proof. Just
No, I understand, but no, but the built-in find equational proof function, right?
yeah, there's gonna be no duplicates there.
Okay, let's take a look at this thing here. So let's look at this, and then let's do your proof graph, proof object to token event graph. Okay, I don't understand this. It's not using by substitution. I'm completely confused here. And it's got many more events.
Oh, too bad. We just found it quicker. That's it.
Yeah, okay, fine. But okay, so how do we turn this one around to be one that doesn't end in the true result? Right? How do we turn this around to be the same type as this?
Just, well, in this case, you can reverse the URLs.
No, you can't. No, you can't. With this,
You just assume that you have an additional axiom d equals d. Not all URLs, but that like.
okay, well, let's figure out how to do that. Okay, hold on. Just start saving this.
It's going to be just like a graphical reversal. You don't actually have to like reverse the positions and how your rules apply, right? Graphically, it's easier.
Well, what do you mean? Because I'm looking for something which is going to look like this, where we start from a equals b dot a, and we end up with this. Not that this is at the top.
No, just, well, you have to use your like identity there as an axiom too.
Yeah,
If you
okay,
want to
fine.
use the same events.
Okay, but so I don't understand. Are you saying that I should add as an axiom a equals a? It's going to be tough to do here. Do you understand what I'm asking? I'm trying to make a picture that looks as much like this picture as possible.
Well, we already done something like that. Just reverse those arrows on the bottom
Which arrows?
that not come from the axiom.
Well, just the staircase, so to speak.
Yeah.
These arrows.
Yes.
Yeah.
Okay, how do I do that then? We say basically we want an edge list of this thing. Is that what I want to do?
Yeah. And do something like accept your axiom on the left hand side. As your pattern.
Wait a second. So what are you saying here? So you're saying I want to reverse some of these edges. Well, as what pattern? Where?
Well, you can specify for the edge list a pattern of edges what you're looking for. So you just have accept your a equals ba goes to blank. That's it. And you just reverse those edges.
Okay. So now I say reverse those. Well, so I say in here, I might say PO equals this. Okay, so now I would say edge delete
Yes.
PO comma, and then let's say okay, edge delete PO comma percent edge, what is it called? Edge add or something?
Yeah, edge add. Yep.
Okay, now how generally can we do this of reversing edges like this? And is that a feature of this thing being a bisubstitution?
No, I don't think so. Well, graphically, I think you can do it always. You just, those events are going to be tricky if you actually want to extract information what the hell happened there. But if you could just indicating visually what happened somehow, then we can do it.
Okay, but so what's the general case of arrow reversal? Okay, so here what we're saying is after 2 steps, the statement shows up in this entailment cone. Okay, fine. There are multiple paths. So identifying that subgraph, that's this thing here. Oh my gosh. Percent 16, comma, percent 23, which is a subgraph. Or do I have to say subgraph of percent 16?
Yeah.
Okay, where is it?
Maybe edge list or something. I don't know. Is it not empty? What is 16? I just don't see this 16.
That's that one here.
Oh yeah. Oh, okay. That's the
Well, that's not encouraging. Or maybe I got the wrong. No, that's by substitution there.
maybe try without some graph. I think it because I add some edges. It's having trouble.
I see.
Do have something like extend graph. Oh, because it's a list.
What's
Percent
the
23. Percent 23.
Oh. Well, okay, let's just look at what we're trying to do here, okay? So we're saying, starting with a very simple axiom, we get the entailment cone shown here.
Oh, I get it. You also two rule fixing this graph. That's why.
Which one? Okay, well, hold on. Let's this very simple axiom. Okay, get the entailment cone, blah, blah, blah. Okay, there are multiple paths. Let's drop the blanks here. Do we have a good way to do that? What's your way to do that?
Symbolified.
What do we do here?
Vertex replace. What do you want?
No. I just want to not display the blanks.
Well, then vertex replace and symbolify patterns.
Yeah. Symbol.
Wait a minute. Do we have to do that whole thing? I thought we had a much simpler way to do this.
So two rule fix actually is doing the same thing.
Okay. Okay, so I don't know, we should probably show the one without blanks. It's just the blanks just make it hard to understand. Shows up in this interment code. There are multiple paths to reach the statement. Well, no. Shows up in this entailment code. Where we're indicating the subgraph that leads from the original axiom to this statement. And we have to highlight that subgraph. Extracting the subgraph, we get, now that's this thing here, which we can view as a proof of the statement within this axiom system. But now we can use traditional automated theorem proving to get the same result.
Automated theorem proving.
Well, to get, but now we can use, but now we can also, but we can also use, which we can view as a proof, as a selecting the subgraph we get, which we can view as the minimal proof, as a minimal proof. But now we can also use automated theorem proving and find equational proof to get a proof of the same statement. Here's the result. And in this case, here's the result we get. Okay. Here's essentially the result we get. I don't know how we say it, but this, okay, so let's look at this. So now we've got proof object. Now I don't know how we should describe this, because we're going to say how do we get rid of that stupid hypothesis one thing?
I think I have it already. Actually, just use vertex label. Blank arrow none.
Okay, so here, and by the way, those should be by substitution colors.
Yeah.
Okay. So now what's going on here? Why is this different? Why is this one so much longer? Is that right? What happens when we go to other cases? Actually, I mean, there's an argument that what we should actually show is this, because okay, we got to get rid of that. Does this have the same options? Oh, for God's sake. Well, okay, first of all, those are by substitution things, and that's not right. But that's a minor issue. Right?
What do you mean
Yes.
those are by substitution?
They should be red. Yeah, it should be red.
Shouldn't they?
Why?
Because they're by substitutions, not substitutions, aren't they?
They are substitutions.
Oh,
I thought the whole point was that this is using the whole paramodulation thing and so on.
Well, when there's a critical pair lemma, then yes.
right.
Well, so should I be using up here?
Substitution.
Should I use substitution for these?
Might make them easier to compare.
Well, that's the substitution case there. Okay, so in this case here, okay. But now we can use traditional theorem proving to get a proof. Now let's use proof of the same statement. What we get. But now let's use traditional theorem proving to get a proof of the same statement. What we get is, okay. So now we have to explain what's going on here. I'm also really confused about why it's so much longer and whether that's typically going to happen or not. I mean, don't we have examples where we got the exact same proof?
Yeah.
Right, so we probably use that example. I mean, where do we have the examples with the same proof? And then we were trying to find examples where we would get, right, so the structure of this needs to be, okay, we're going to show, first of all, an example where we fish the thing out of the entailment cone, and we show we get essentially the same proof, okay?
Okay.
Okay.
I think we Nick, this is the middle of your night. I think it's unfair that you're whatever it is. I don't know.
That's my morning.
Well,
Yeah,
I
you sound
suggested
very
that we
tired.
I suggested that we meet at 7 p.m. Stephen's time, but Nick said, no, I'm available. I'm available.
All right, okay.
So we both
I have to get
woke
myself
up
some
early.
lunch in a moment. Yeah. So
You have
I
to
mean,
what?
I have to get some lunch for 5 minutes. I mean, 2 minutes or whatever. And I will have to go in
half an hour.
a little less than that. So but the roadmap here is the following. We need to find an example. So let's write down the roadmap here. Okay. Map. So we're going to find example of entailment cone where we can fish out a proof that is the same as ATP.
Okay.
Probably using only
Substitution.
Okay, then more complicated case where by substitution is needed. And then, okay, so in this case, okay, now we have to say, okay, then turning the proof around to make it more like entailment as opposed to the proving true thing.
Yep. Yes.
Okay, so that's what we have to, okay, so now what else do we want to do? We want to talk about cut elimination. At some point, we want to talk about much greater efficiency of finding a proof when one knows where one's going. Okay, I had those Amazon jobs, right? Look, listen, I got to make myself some lunch. I'll be right back, okay?
Okay.